In the next section, I will present some practical examples of how the amide 1 band can be used to monitor the structure of proteins. The sensitivity of the amide 1 absorption to secondary structure makes it possible to study protein unfolding and misfolding with infrared spectroscopy. The left-hand panel of the figure shows the typical spectrum of a small beta sheet protein at low temperatures, with the main peak at low wave numbers, here, and a shoulder at higher wave numbers. When the protein unfolds at high temperatures, here, the spectrum changes to a broad, featureless band which is characteristic of unordered structure. The situation is different when the 3 proline residues in the primary sequence are replaced by alanines. The starting spectrum, here, still the same, a typical beta sheet spectrum. However, the final spectrum is very different. This one. It has a very pronounced band at even lower wave number than the initial structure and a more pronounced high wave number shoulder. These features are again typical for beta sheets. Because of the low wave number of the main band, one can conclude that the sheets contain many strands or are very flat or both. This is typical for the intermolecular sheets of protein aggregates. Thus, the replacement of 3 proline residues leads to a dramatic change of the structure of the denatured state at high temperatures. The latter example demonstrates that infrared spectroscopy can be used to monitor the aggregation of proteins. This is an active research field because protein aggregation occurs in neurodegenerative diseases and may be the actual cause of these diseases. Before continuing with applications, I need to explain a method to extract more information from the amide 1 spectrum than what is possible by just looking at the absorbance spectrum. The background is that the amide 1 band is usually quite broad and components from different secondary structures are hard to identify. To reveal more information about the underlying component bands, the second derivative of the absorbance spectrum is often used. The second derivative of a single absorption band has a minimum, where the absorption band has a maximum. The negative band of the second derivative is narrower than the corresponding absorption band. In a spectrum that consists of several component bands, the second derivative can therefore reveal the positions of the component bands better than the original absorbance spectrum. A disadvantage are positive side lobes in the second derivative spectrum that might be confused with real component bands in a complicated spectrum. The slide shows the infrared absorbance spectrum of pyruvate kinase as an example. The absorbance spectrum on the bottom is rather featureless. In the second derivative spectrum on the top, the component bands are more obvious. Spectral positions of the minima correspond to the spectral positions of the component bands in the absorbance spectrum. These positions are indicated by the vertical lines in the figure. With this knowledge, we can now look at further applications. In this slide, we have used the amide 1 absorption to check the quality of recombinantly expressed protein. The slide shows second derivative spectra of the membrane protein calcium ATPase, also named circa 1a. The black spectrum is the gold standard, which is the spectrum from a rabbit muscle preparation. The blue spectrum is that of a recombinant preparation. The highlighted region in the beta sheet range indicates that the beta sheet structure of the 2 proteins is different. This is due to partial aggregation of the recombinant protein. Notable is also the stronger lipid absorption at 1740 reciprocal centimeters. Compare this band to this band, which indicates a higher lipid to protein ratio. The next example concerns antibodies, which are increasingly used as protein drugs. To guarantee their intended medical effect, they need to be stable during transport and storage. Structural changes associated with, for example, temperature changes, pH changes, or freeze-thaw cycles can be studied in the amide 1 spectral range. This slide illustrates the sensitivity to pH as an example. Second derivative spectra of an antibody at different pH values are shown. The spectrum at pH 12 on the top is clearly different from the spectra at other pH values. Also at pH 3 there is a change at 1628 reciprocal centimeters here, likely due to aggregation of the protein. Thus, the structure of this antibody is affected by the pH value.